Let's begin. Welcome the members of the Kaggle and the UBC. Here is the report of the second place solution for the UBC-OCEAN competition. The agenda of the report is as follows. First, a brief introduction of our team members, then an explanation of our solutions, implementation details, and some conclusions. And finally, a QA section. Our team consists of 4 members. Among that, Shuloden is graduate with the master degree from South China University of Technology, majoring in computer vision. And Xinzhen is graduate with master degree from Huazhong University of Science and Technology, specializing in risk control and natural language processing. Xiaoling is graduate with the master degree from Beihang University, specializing in risk control and natural language processing. ZZNZNB is studying at the South China University of Technology in the first year of the master program, majoring in computer vision and pathological image research. Among them, Shuloden, Xinzhen, and Xiaoling work at the N group. Although not all members of our team have experience in the study of pathological image, they all have a strong background in machine learning and deep learning. Now let's take a look at the overall process of our solutions. You can briefly summary in 3 stages. Cropping patches, extracting features, and training the model. The feature extractor is frozen, and only the MIL model needs to be trained. Therefore, everything before getting the patch features can be considered as the data pre-processing. Next, we will provide a detailed introduction of each part. When cropping patches, we operate on a thumbnail image. Firstly, we generate a series of equidistant gray coordinates and consider them as the top left corner coordinates of the patches. Then we filter the patches, removing those with a mean pixel value less than 10 or greater than 245, thus removing the paths belonging to the background. After that, we save the remaining coordinates as a list to be used as a variable in the PyTorch dataset class. During inference and training, we get the patches from the original image based on these coordinates. We use thumbnail image for this step for 2 reasons. First, patching filtering does not require high resolutions, only a rough color judgment. Second, cropping on the original image is time-consuming, and setting the final coordinates on the thumbnail image can significantly reduce the time spent coding on the original image. When extracting features, we use a pre-trained vision transformers designed for pathological image analysis as the feature extractor. The safe coordinate list enables us to compute the patch image features in parallel, thereby enhancing the feature extraction rate. Based on our previous experience, models pre-trained on pathological image tend to focus more on the detail within the pathological image, resulting in more easily distinguishable features. Additionally, Vision Transformer is currently one of the most popular models, capable of supporting large-scale image pre-training. Some experimental results indicate that Vision Transformer outperforms convolutional networks, and that pre-training on pathological image improves performance compared to that one pre-training on the natural image. The resolution of pathological image is too large to be directly input into the network, so they must be processed in patches. The key is how to combine different image patches to obtain the final conclusion. ABML and DSML use a weight sum approach, while TransML use a transformer-based approach. Next, we will provide some additional details on the implementations. First, let's talk about the external dataset. We use 2 sets of external datasets, setting those class that do not include in the official class as other. The external dataset have improved our performance. Here is our training strategy, with some key point being, for class with limit date, we perform 3-time oversampling and perform 5-time oversampling for other class. Then stratified sampling is applied to image of different shapes. Finally, we arrange the model parameters from the 12th, 15th, 18th, and 21st epochs to provide overfitting. During the inference, we merged the result of 4 different models, including 2 feature extractors and their corresponding MIL models. The weight were determined based on individual performance. In order to complete the prediction within 12 hours, we did not use all patches, but instead employed strategic sampling based on the image size, aiming to use as many patches as possible without exceeding the time limit. Finally, let's summarize. Firstly, what are our design principles? We basically follow the mainstream methods in academic community while also considering simplicity. We omitted some steps that did not significantly improve performance, enabling us to complete the computation with just a few code files without the need to build a complex framework. Compared to other high-scoring solutions, our approach can be considered the most simple. Second, the biggest challenge we faced in the computation was runtime and memory limitations. During the first half of the computation, we used FemNow image, but later find the right method to perform prediction using the original image. However, in order to merge more models during prediction, we had to compress memory use and reduce runtime in the later part of the computation. As for why we finally succeed, 2 reasons stand out. Firstly, we had experience in the study of pathological image, enabling us to quickly and accurately process the data. Competitors lacking this experience may not know how to handle such high-resolution image. Therefore, our professional advantage enables us to distance ourselves from other competitors. Secondly, we had experienced engineers, although they not focus on image research. They play a significant role in processing the feature and merging the model. Therefore, teamwork was also an important factor in our success. This is all my report today. Next, we will have a Q&A session. You are welcome to ask any question.